This is Hexium OS. It's a custom operating system I wrote from scratch using Rust and x86 assembly. It's got a custom file system, a text editor that's definitely better than them.
Man, shut your
It plays Snake, and yes, it can run Bad Apple at 15 frames per second. There's no Windows here, no Linux, no Mac. This is bare metal code talking directly to your hardware. But before we get to the core OS, we have to go back to this, a blank file. Because honestly, when I started this, I had absolutely no idea how a computer actually boots. So I did what any senior engineer would do. I asked ChatGPT for help. And I quickly found out that the OS development community loves to gatekeep. If you ask how to write an OS, 90% of the answers are people telling you not to. They say it's too hard, it's a waste of time, or you need a PhD in computer engineering, which naturally made me want to do it even more. Eventually, I stumbled upon the Holy Grail, the OS Dev Wiki. This place is basically the ancient library of Alexandria for system programmers. It broke down the massive, scary concept of an operating system into actual manageable components. I realized it's not as scary as I thought. I just needed three things: a bootloader, a kernel, and a way to talk to the hardware. First up, the bootloader. When you press the power button, your computer is dumb. It has no idea what Rust is or what a kernel is. It just looks for the very first piece of code it can find on the disk to tell it what to do. Most people use grub, but since we are doing this from scratch, I wrote my own bootloader in x86 assembly. This is a bridge between the hardware and our Rust code. This boot assembly file has one job: convince the computer that we are a valid operating system. To do that, we have to include this specific magic number. If the hardware sees this number, it agrees to load us. Then we set up a small stack, basically a scratch paper for the CPU. And finally, we make the jump. We call kernel main. This exact moment we go from assembly to Rust. But there's a catch. Rust doesn't know where in the computer's RAM it's supposed to live. If we don't tell it, it might try to override the BIOS or the video memory. So we use a linker script. It organizes our code, our data, and our read-only constants, so the bootloader can find them. Now, normally to print text, you would use print or console.log, but we don't have an operating system to listen to those commands. We have to do it the hard way, through memory mapped.io. It turns out the video card is constantly watching this specific address in memory. If I write a byte to that address, it doesn't get saved to the RAM. It gets displayed directly onto the monitor. The screen is just a grid of 25 rows and 80 columns. Every cell takes 2 bytes, one for the character and one for the color. So I wrote a simple VGA writer that loops through a string and puts these bytes into the video memory one by one. I compiled the kernel, booted QEMU, and it worked. We are officially printing to the screen, but it's just plain green text. It needs a little... much better. But there's a problem. It looks cool, but it's completely useless.
hell no, man. What the fuck, man? Get your ass on, bro.
I'm matching my keyboard and nothing is happening. Because right now, the CPU is just spinning in a loop, ignoring everything else. To fix this, we need interrupts. Basically, we need to tell the CPU to stop whatever it's doing when a key is pressed. This requires setting up an IDT, interrupt scripter table, and a PIC, programmable interrupt controller. And let me tell you, interrupts are a nightmare. If you miss up one line of assembly here, the computer doesn't just give you an error message, it just shits itself. But after hours of debugging the IDT, I finally got it, a working keyboard driver. You can type, delete, and even execute commands. But currently we just have the echo command. Okay, we have a shell, we can type commands, that's cool and all, but an OS isn't good until you can game on it. So I decided to board the classic Snake game. Honestly, after a nightmare of setting up interrupts, this was actually really easy. The game loop just checks the keyboard states, updates the Snake position, and redraws the screen. And it runs flawlessly at 15 FPS. But I wanted more. Sure, Snake is cool, but it's just a few characters moving around. I wanted to see if I could push this VGA text mode to its absolute limit. And there is only one true benchmark for any display technology, and it's Bad Apple. But Hexium OS, where it stands, doesn't have a video codec. It doesn't even know what an MP4 is. And I don't really feel like writing one on my own. So I wrote a Python script to cheat. The Python script takes the original video, sizes every frame down to 80 by 24 pixels, and converts the brightness of each pixel into an ASCII character. Dark pixels become spaces, bright pixels becomes hash symbols. Then it spits out a massive raster array containing every single frame of the animation. We compile that data directly into the kernel, play it back using the system timer to keep the frame rate steady, and it works. We are streaming video on a bare metal OS that doesn't even have a graphics driver. Now I want you to listen carefully. There is no audio, and watching a video without audio is just boring. So I tried to hook up the PC speaker to play the audio, and yeah, it didn't go well. So I decided that for the sake of my own sanity, Hexium OS wouldn't have any audio. So we are going to pretend the audio thing never happened. At this point, we have a cool toy, but I wanted an OS that I could actually use. That means we need files. I built a custom in-memory file system. It supports directories, reading, and writing. The only problem is that it lives entirely on the RAM, so if you turn the computer off, your files are gone forever. And to edit those files, I built this. A full-screen text editor with scrolling, cursor navigation, and a status bar. Not to brag, but it's better than Vim, because unlike Vim, I actually know how to exit. So that's Hexium OS. It still has a lot of bugs and missing features, but I can't be bothered enough to fix them. The entire source code is on GitHub if you want to poke around. If you enjoyed this, thanks for watching, and I'll see you in the next one.